Welcome to Have a Life Teaching, the podcast designed for educators who are dedicated to enhancing their teaching practice and creating a positive impact on their students' lives. In each episode, we'll dive deep into the world of education, exploring a wide range of topics related to curriculum, instruction, and assessment in K-12 schools. Together, we'll learn from the brightest minds in the education field. So if you're a passionate educator who's ready to take your teaching practice to the next level, join us as we explore the exciting world of education. My name is John Shimbari, signing in and saying, let's have a life teaching. Hello, everyone. Welcome to another episode of the Have a Life Teaching podcast. One of the challenges in math is making it approachable, more open for students. That is why if you go into math classes now, you'll see textbooks are featured around this. The concept of CRA, teaching math conceptually. That might be in an elementary or a middle school, having students use blocks, using actual number lines to have a clear understanding that the numbers they're working with are not just these abstract numbers, but represent something physically. Then the next step you might see math classes using now is having students represent what they were just doing physically through pictorials, say drawing bar graphs or drawing number lines and representing those numbers visually. And then lastly, not that it's not important, the students still need to know formulas, they still need to know abstract ways of solving math problems, but you bring it in last. Think of CRA as a framework to gradually release the control and the learning of math to students. Another way in gradually release learning to students would be to look at a framework known as See It, Say It, Symbolize It. Today, I'm really excited to have as my guest Patrick Sullivan. Patrick is a professor at Missouri State and the author of this great book, See It, Say It, Symbolize It, Teaching the Big Ideas in Elementary Mathematics. And what we're going to be talking about today is having students seeing the math, saying the math, and then symbolizing it. Patrick, thank you so much for joining us.
Thank you for the opportunity. I'm looking forward to our discussion tonight.
Patrick, how did math instruction become a passion for you? And why do we need to approach the teaching of math differently than, say, traditionally, maybe the way you and I learned it as students?
Throughout my 30 years in teaching, I've reached points where you're standing at the board and you're wondering truly how many students are able to make sense of what you're doing. And knowing full and well you're writing on the board or you're doing something and you're really wondering, what are they really thinking about what I'm doing? And when I started to ask that question, unfortunately and sadly, there wasn't a whole lot of thinking going on. There wasn't a lot of depth to those thoughts. About 5 or 6 years ago, when I started to teach developmental math at the university level, I realized just how little these students knew about some of the big ideas in elementary mathematics. And they could tell me some computations or ways to do things, or maybe what they remembered in terms of some algorithm, but they really didn't have a meaningful understanding of numbers and operations. So that's really, for the last 5 or 6 years, that's been a passion of mine. And I've spent a lot of time listening to students, not only elementary students, but college students who struggled with math and other adults, and thought there's got to be a better way. We're missing something here. What would this look like in my perfect world? What would this look like for me if I was going to have an opportunity to change what I consider this insanity right now of having so many people walking into life and no problem telling me they're not very good at math? It's not trigonometry, it's not calculus we're talking about, it's numbers and operations.
I'm glad that you said that, because one of the reasons I talked about the importance of CRA, conceptual relationships, and then abstract thinking when it comes to math, is because, to your point, I think the way we learned math was starting with the abstract. rather than starting with the conceptual understanding and then making those representations of
Right.
what the meaning of math actually is. How do we then help our students make this meaning
Mhm.
in what they're learning? Because as you said, Patrick, even your college students might not actually know the meaning of what those numbers represent.
That illustrates one of the main points I make is when we look through, it's about looking through symbols. And the whole point of symbols is there's this compactness to it. And so, but what do we see when we look through it? And I'll give you a simple example. What do you think about when you see a symbol 1.6 over 2? What things are cued in your mind when you see a symbolic form of something like that? And I had just talked to a student about what was 16 divided by 2. She was able to talk to me a little bit about what that meant, but everything was about what goes into moving the decimal and all those things. That's not really what we want students to look through and see, because she could tell me that 16 divided by 2 was 8, but then when I wrote 1.6, again, I'm saying that intentionally, divided by 2, she froze up and couldn't do anything with it. And I'm thinking, so I started to push on, well, what does the 1 represent? What does the 6 represent? And this goes to what I'm going to talk about a little bit later about superpower understandings, is that she say 1 and 6/10, but she couldn't remember the algorithm. But the minute I said, well, if it's 1 and 6/10, what is it 16 of? She said, it'll be 16/10. Well, essentially, you're doing the same problem again. It's the same 16 divided by 2. It's just your unit is different. And then she's like, well, why didn't anybody ever teach me that? That to me is low hanging fruit. So that's an example of a situation where I want students, when they look through those symbols, to have a lot behind it, because that's the whole point in the process of those symbols. It's a compactness, but there should be a lot of understandings that are behind it.
And also, Patrick, another very simple example could, even for the younger grades, could be 1 plus 1.
Yeah,
Or what does that plus sign
yeah,
symbolize? It
yeah.
symbolizes you're taking one item or one
Mhm.
group and you are combining it with
Yes,
another group. Am I
yes.
understanding that correctly?
You are dead on, because what I love about that is, let's just go with this. If we had 1/5 and 1/5, we would have 2/5. If we had 1x and 1x, we would have 2x, or two groups of x. So one group of x combined with another one group of x is two groups of x. To me, that's a unifying idea. But as you said, that plus symbol, there's a language that goes behind it. It initiates what we consider a combining action, which is addition. Exactly.
There's a lot there that we could unpack. As you
Mhm.
were talking about with that student, you visualized that fraction, that
Mhm.
1.6 over 2.
Again, I said the 1.6 because oftentimes we talk about it that way. But what's hiding behind it that we don't really put emphasis on is there's a unit. So in the decimal number system, the 1, what's hiding behind it is that it's a unit, 1 unit of 1. And then what's hiding behind the 6 is 6 units of a tenth, or 1/10. And so the idea is that, again, this is speaks to a lot of the superpower understandings I might talk about a little bit. But one of those superpower understandings is that numbers are a tethering of quantities and sizes of units. And then there's also what I would consider this equal exchange. I can have 1 and 6/10, but that's also the same as 16/10, because 1 is equal to 10/10. That's the equal exchange. So I now have 16/10. So I can think about, if I understand that 16 divided by 2 is 8, that's really 8 1s. We're hiding that. But then I also have 1.6 over 2. That's also 16/10. So I'm still doing the same operation, 16 divided by 2. So there's really actually three, what I would consider superpower understandings in that one problem, because I would say in my world, 16 divided by 2 and 1.6 divided by 2 are what I call analogous problems, because they involve the same actions, but on different sizes of units.
And that
So
would be one of the superpowers.
yeah, that's actually, there's three. The three for early mathematics is in that one problem. I didn't intend for it to be that way, but it kind of worked out. First is that we see numbers. We don't just see, keep saying 1.6 because I know that's the way to say it the easiest, but really if I was teaching it, I'd say 1, 1 and 6 tenths. But it's not just 1, 1 and 6 tenths. It's also, I can think of that as 16 tenths. I can think of that as 160 hundredths. I can think of that in any way I want based on what it is that I want to do with it. That's going to help me flexibly think about this idea mentally. That's the first one. That's the tethering, thinking about numbers as a tethering of quantities and size of units. And then the second one was being able to make those adaptations is what I call equal exchanges. And we've done this all the time with money. You go to the bank and you hand somebody one $10 bill and you want something equal back in terms of ones, they're going to give you 10 ones back. That happens throughout mathematics. More formally, we call that equivalence, but the idea is that this is all happening, that even when we talk addition and we carry the one, what we're really doing is an equal exchange. And it's language that we can use throughout mathematics. Getting a common denominator is about getting the same size of unit. It involves an equal exchange. Being consistent with that language and we can connect it. And so math just doesn't seem like a bunch of disconnected parts, but it's this connected entity around these same ideas, just like we talked about a little bit earlier with addition. My third superpower that I talked about again was being able to see problems as derivations of the same thing that we've already done. It should not be a jump for a kid if they understand numbers in terms of quantities and size of units. 16 divided by 2 shouldn't feel a whole lot different than 160 divided by 2 or 1.6 divided by 2 or 0.16 divided by 2 because they're all 16 of some unit. And as long as we're being aware of what that unit is, those problems are analogous to each other because you're going to do the same thing.
Patrick, we talked about three of these superpower understandings when it comes to math. What are a couple others that you think elementary school teachers should know?
This one is huge. The one that's missed out on a lot, and I'll set this up. A lot of the research, we've done research with fourth graders, we've done research with seventh graders, and we've done research with adult learners. I have data from all 2,500 adult learners, freshman students in college across all classes. But a question we typically ask is Tyler ate 5/6 of a whole medium pizza, and CJ ate 7/8 of a whole medium pizza. Who ate more pizza? 25% or more of students will tell us that they ate the same amount. And what that tells us is they're not attending to the size of the unit. Fractions are not thought of in terms of units for them. So that next superpower understanding is understanding the meaning of a unit fraction. And this has a language component as well. So when I say 1/4, there should be a relationship between 1/4 and 3/4. 3/4 is three groups of 1/4, but I can't get anywhere with fractions until I understand the meaning of 1/4. Part of it is thinking in terms of language here. What's nice about it, and this is a big rant I have, I think we really mess students up in third grade when we use the standard fraction notation with students. Because if you think about, let's say you write in standard notation 1/4. The problem is with fractions is up until fractions, students have seen numerals as a quantity, 100, 100, or 400. 4 represents 4 and the unit's 100, 4/10. But when you put it in the denominator fraction, the numeral becomes, and it's the only time in mathematics it happens, the numeral becomes a unit. And so up until with the decimal number system, the unit's hidden by the place value. So you don't really see it there unless you write it. But depending on if it's in the numerator of fraction, like 4/5, that 4 is a quantity. But if it's in the denominator, it's now a unit. And that messes kids up because we use that standard notation with the numeral representing the numerator and the denominator. And so what happens is the students rely on their whole number understandings. They don't deal with the fact that that 4 in the denominator represents the size of unit. And there's also another reason why using the word label is so important is that if you think of the word fourth, fifth, sixth, it doesn't work for half or third, but fourth, fifth, sixth, seventh, eighth, is that morpheme THS we can associate with the equipartitioning action. And then Equipartitioning action, how many times we do that equipartitioning is the prefix of the word. So you got force. How many times you're going to partition that thing? If we're talking about a whole or whatever, you're going to partition into 4 equally sized pieces. And then a fifth, same idea. So really emphasizing that idea that THS is a morpheme that, and we associate that with a particular action. But oftentimes our students are not walking away from their initial experiences with understanding that there is a unit associated with fractions. And in fact, many times they see two quantities. They see a number of partial pieces. Let's say an example of an area model, a missing piece area model. So imagine that you've got a grid that's been shaded in 7, and then there's 8 total pieces. And so they're looking at as what I call a dominant part whole understanding, where they see the number of things shaded and they see the number of total pieces. And there's no focus on that emphasis that there's a unit involved. And they carry that with them a long time, we have found in our research. It's crucial that this connects with the Common Core Standards, 3rd grade, that students need to see fraction as numbers. And that means they need to see it in terms of a measurement, that 5/8 is not 5 out of 8, but it's 5 groups of the unit of 1/8. So many of our students walk away without that. I blame a lot of the curricular resources for that because we're not attending to that. And then the last power understanding goes up the ladder a little bit. It's probably more 5th grade, maybe 6th grade. But seeing ratios, the two multiplicative relationships that are embedded within ratios. Let me give you an example of one here. 2 to 10. You've got 10 blocks and 2 of them are red. Well, you want to create an equivalent ratio. It's going to be 4 to 20, for example. Well, we got within the space, we've got a doubling. 2 times 2 is 4 and 2 times 10 is 20. But we also have that the relationship, there are 5 times more total blocks than there are green blocks, or 1/5 times total blocks than there are green blocks. Being able to think about those multiplicative relationships instead of having students cross multiply, jump right to that. But it's so important that students see that. I think of ratios as still a multiplicative relationship. You've got the ratio 2 to 10, but you have another one, 2 groups of 2 to 10 is 4 to 20. And so that's the 5th, what I consider superpower understanding. But those first 4 are going to happen from the very beginning, grades 1, grade 2, grade 3. And if they're not there, it's very difficult for students to have a dynamic and flexible understanding of numbers and operations.
In terms of these superpowers, it makes sense to me that students need to be able to, again, see it, say it, and symbolize it in multiple ways. And that these superpower understandings, if teachers know what they are, then they could start teaching their students to look at math through the prism of these superpower understandings.
Absolutely.
That begs my next question, Patrick, which is, what would a typical modeling of math look like with any one of these superpower understandings or combination of superpower understandings?
For example, let's imagine that we had base 10 blocks and I wrote a problem up 38 plus 45, and I wanted you to model that on the place value grid. Now, what's different about my place value, Matt, is we bring the units, we can either write them in or you have little pieces that you put there. But so bottom line is, I said, what, 38 plus 57, I think, something like that. But so what you'd have is, okay, I'm going to model. I need 3 10s and 5 10s. I need 8 1s and 7 1s. And they're on the mat. And I've got them under my place values, 10s and 1s. I can now take those 10 1s, and I can equally exchange that for 1 10, and I can do that operation. And now, here's the crazy part. I can go through and do that operation, finish the problem. But the crazy part is, you know what? I'm going to remove those. My units are no longer 10s and 1s. Let's put 110 as the 2 units I'm going to use now. Or let's put up 1 and a 10th as the 2 units. As long as they're consecutive units, I'm essentially doing the same operations. I'm going to bundle together 10 of whatever it was I had on the right, let's say 10 tenths, and now that's going to become 1 1. So now my students don't just see 38 plus 57, they see 380 plus 570, they see 3.8 plus 5.7, and they realize, wait a minute, I don't have to learn something different for each of those because it's the same action. I just have to pay attention to the unit that is represented by each of those numerals.
What would be some of the questions a teacher could ask students to get them to see those different units as the same mathematical process or procedure?
Okay. So one of the things that we commonly ask students in the addition example that I gave you was you took these 10 what? What are those? For example, in the first example I gave you was 38 plus 57, I think that was.
Mhm.
What do you have there? What are they? Well, I have 10, what's the U 10 of what? 10 ones, and I moved them over here. You exchange that. You actually took them off the board and gave me a rod, which what's that rod? That's 110. Okay. So now I've got that. So we've done that. So now I switch out the units and I say, okay, we're going to switch the units. We have the same things on the board, 3 and 5, 7 and 8 over here. And let's change the unit. And so now it becomes hundreds and tens. And so now we do that same action. Okay, 10 what? What are they? Well, 10 tens. Okay. And what are we exchanging it for? 100. Okay. Now we've done that. So really emphasizing, pushing on, and I think the biggest thing for teachers that talk about the unit, make the unit as explicit as you can. So even if your textbook writes addition problems vertically, let's say again, it's written vertically, the standard notation, 57 plus 38, draw that line down the middle, those lines, break those up and write the unit that goes above those. But make it very explicit that you're still dealing with it. You don't have to do it forever. Make it accessible and obvious to students, make it visible, I guess is what I'm trying to say. That's going to be really critical. And then you ask students, once they get used to this, you can ask them, the key is to put problems in tandem. In worksheets, you start to ask different questions. How is 38 plus 57 similar to 380 plus 570? Or how is it different? How is 3.8 plus 5.7 similar or different than these other problems? But you group problems differently because you're wanting students, again, to look at, again, I don't emphasize this a lot in the book, but we're talking about mathematical practices. We want them to see structure. And by seeing structure, we're working at helping them make connections. Those analogous problems, the emphasis on equal exchanges, the emphasis on the tethering of quantities and size of units is all about making that structure be what's most apparent and less emphasis on the procedure and doing a bunch of problems that way.
Patrick, we've spoken a lot about addition, adding fractions, adding some numbers that might represent different units. You were just giving the example of 38 plus 57. Do these strategies, do these superpower understandings, do they relate to the other operations of subtraction, multiplication, and division?
My argument is it's the same way you do some of these other operations. So obviously subtraction is related mathematically to addition. We can do similar things. The only problem here is it's decomposing units of 10 to create an example off the cuff here. Let's say we're taking 2003 minus 97. Well, we normally say 2003 minus 97. We can do a little tweak here. We can think about this as 2003 as 200 tens and 3 ones. And then we're subtracting 19 tens and 7 ones. I'm going to do a little decomposing. Instead of 200 tens, I'm now going to have 199 tens, and now I have 13 ones. Okay, well, 13 ones minus 7 ones, that's no problem. 6 ones. Now I have 199 tens, and I'm removing 19 tens. Piece of cake. It's 180 tens. I'm done. So I don't have to carry anymore. I don't have to do any of that canceling. I can think about it. I don't have to write it all down even because I have this power in my mind of how I think about these things mentally. Those things play out. Very similarly with subtraction, with multiplication, 6 times 8, we know that's 48. Well, guess what? If it's 6 times 8, 800, it's 48 hundredths. We just have to make sure we find out where we line up our numerals. The decimal system is beautiful because it lines up perfectly. 6 times 8 tenths is 48 tenths. 48 tenths, put that 8 in the tenths place, 4 in the ones, done. You got it. Because you've got those 48 tenths, and every 10 tenths is 1 1. Again, another equal exchange. But now, again, I'm just doing analogous problems. Now, what it gets a little weird, but it's still the same idea, is 6 times 8 fifths. 6 times 8 fifths is, guess what? 48 fifths. It's just now that I'm talking about fifths, the recomposing action happens after 5. So I have to keep track of that. And so now I have 9 whole and 3 fifths. I don't even like to call them mixed numbers. The only reason they're mixed is because we're talking about the result in terms of two sizes of units, 9 ones and 3 fifths, as opposed to one, when we say 48 fifths, it's not improper. It's just we're talking about it in terms of one unit. That's that. And then the same is true with division. If I think about 6 divided by 2/3, if you think about 6 ones as being 18 thirds, and again, another equal exchange, 18 thirds divided by 2/3 is analogous to 18 divided by 2. It's just we're talking about a different unit. If we can help students make those associations by how we scaffold problems and bring problems together so they can see similarities and differences between ideas, it opens a whole different world of mathematics up to them, that they're not just plugging and chugging through doing these problems without thinking about structure, because it is the structure that underpins that. It's this idea that helping them see the structure by how we put problems together, tandem. I love putting a whole number problem together where, let's say you have 18 sandwiches and each student is going to eat 2 sandwiches. How many students can we do that with? It's the same thing as if I had 6 sandwiches, I gave each student 2/3 of a whole sandwich. How many students could we feed? It's the same structure of the problem. We're just using a different size of unit. Tandem problems like that really help because students can begin to associate what they already know about whole number division with division involving fractions or division involving symbols or decimals.
I like this concept of tandem equations because one differentiation strategy that I have found very helpful in math classes, particularly on the elementary and middle school level, are anchor charts and actually visualizing an example of a problem and the
Yes.
way that students can either solve that problem, construct or deconstruct, depending on what operation you're using.
Absolutely.
Could you give us an example of what an anchor chart for tandem problems or tandem relationships might look like?
A lot of times I put a whole number problem on one side, a problem involving fractions next to it on the right side. I want them to see the similarities and differences between, earlier I was talking about 58 plus 37. We'll put a tandem problem and help them see the relationship between seeing 58 plus 37, what they did with whole numbers, is exactly the same as what they do with a decimal, like 0.58 plus 0.37, or 58 hundredths and 37 hundredths. Show them how both those things happen. And then also, I have a couple anchor charts that I've developed, but one is about equal exchanges. And on that, we talk about what does equal exchanges look like with whole numbers. And it's usually obviously going to be 110 for 10 ones, things like that. But then also with fractions, it's the same idea. We call them equivalent fractions, but the idea is still the same. 1/4 is an equal exchange for 2/8. And there's this relationship that happens between the quantity and the size of the unit. But we want those big picture, those superpower understandings as being anchor charts themselves. I've developed a few myself. Here's the challenge with teachers often in terms of professional development. This is new to most of them, but they are ambitious about wanting to bring these things about because they see the power of them. But oftentimes they need reminders of, well, how do I have to talk about this differently? How do I have to think about mathematics differently because of it? It's a lot of work, but it's also powerful. I have students all the time that are just so irritated that they weren't taught this from the very beginning. This would have made math so much easier. I have my college students tell me all the time that you mean to tell me that fractions were always about, addition of fractions were always about getting the same size of unit. Why did nobody tell me that? Now I understand there's a difference between a quantity and a size of unit. I can do things now that I never thought I could do before.
Are some of these anchor charts in the book? What tools would you recommend in the book?
They're not in the book. I do have figures though that show those connections within the book. In chapter 2, I start out talking about superpower understandings, but some of the images I've tried to build throughout the book show some of these relationships. I know when I talk about the multiplication, I use that problem of 6 times 8, 6 times 80, 6 times 800. That is on page 127.
Seeing analogous problems in multiplication.
Yeah. Some of these analogous problems. I have one on page 77 with respect to addition. With multiplication, I have an example on page 127. Some of them are going to be free, but I'm also in the process of developing some curricular resources to rethink what this looks like, because I don't see a lot of resources out there right now that are thinking about mathematics this way, and I have teachers asking for them. So I'm working on building some resources now related to that.
I love that. And what I'll do in the show notes, Patrick, for our listeners is I will link to your Teachers Pay Teacher site. People can check out those anchor charts. You were saying that teachers are asking you for these things. Have you had the opportunity to go out on the road and to work with teachers in using See It, Say It, Symbolize It as a methodology when it comes to teaching math?
I'm just now starting to do some of these things. I've worked with a group called Teachers Like Me up in Kansas City, and I've done a couple trainings with them in some of these ideas, specific with fractions and multiplication. I'm planning on starting this summer. I'm going to launch a workshop in Kansas City and in St. Louis. I'm in the process of doing that. I am starting to get out to do that. I think these are critical conversations. And while I believe strongly in active learning and a lot of the strategies, instructional strategies are out there, I think to truly change the outcomes for students is going to require us to rethink how we see and say many of the big ideas in elementary mathematics.
Now, we haven't talked much about vocabulary within the teaching of math. How should a teacher be presenting that? Because we've been using vocabulary this entire conversation,
Yeah.
even though we're talking about math, tenths, fifths,
Yeah.
numerator, denominator. What are your thoughts on integrating or building in vocabulary?
Part of that is we try to cram it into students without building understanding many times. And so words don't mean a whole lot for me. I made assumptions about so many words that I thought I knew. Why do we use the denominator for the bottom of a fraction? Why is that the word we use? Man, that's a big word. And why do we use numerator for the top? And I went back and realized it's Latin roots, denom, name, numeraire, number for the numerator. And I started to realize we don't need to be so formal with that. Why don't we just call it quantities and sizes of units? Because those are big words that they have meaning to us as adults, but they don't help students, I think, make meaningful connections with the mathematics. I know there's a push to use formal mathematics to talk about like properties, the commutative property or the distributive property. Students need to have real experience with those before we name them so we can make the association. Language is a big deal for me because we talked about fifths and sixths and sevenths and eighths. I don't think we leverage what we talked about earlier in terms of the morphemes and those relationships, the spelled out words as much. And quite frankly, our number system is a little bit of a mess from 10 to 20 because we use 3 different derivations of 10. Some out there will say, well, why do we call it 12? Why not just 1, 10, 2 ones, at least for a little while? Kids are first trying to make sense, so there's more of an emphasis on the size of the unit because we jump from 12 is one derivation, 15 is a different derivation, 20 is a third derivation, and that really slows students down. Let's be consistent early on with giving that language, that appropriate language. The language that I'm focusing on is more about helping them make connections. Formal mathematicians would talk a lot about what I'm saying as equivalence, but why can't we just call it an equal exchange? Because we're essentially replacing equivalently one quantity and size of unit for another quantity and size of unit, making language more connectable to what we're asking students to do. And one of the other words I've used multiple times tonight is analogous problems. And I look for a time where students start using that word. I know I have them when my students start using those terms. Is that an analogous problem to this? Well, why is it or why is it not? Got them then. They're done. I've got them roped in. I think oftentimes we look at the language and we just don't build meaning into it. If we want to argue about it, fine, but words are a form of symbols themselves. And so what meaning are students associating with those symbols? I know some would argue with this, but I call the commutative property multiplication, I talk about it in terms of switcheroo, because what we're doing is if we rotate that array 90 degrees, we're switching the quantity and the size of the unit. More strategically, the multiplier and the multiplicative unit. We need to be clear with students about what things are. We expect them to pick up too many things without making it explicit. I've been emphasizing a lot tonight about the unit. That's a big part of the language that we want students to have. We want them not to just say 120. We want them to say 102 tens or 12 tens or 121s. We want that flexibility, and that's where we're going to require the use of that language that really truly represents what we see happening in front of us.
What have we not talked about, Patrick, that you think it's important for our listeners to know?
One of the things that comes up oftentimes when I talk to adults who have lost hope in being good at math, 90% of the time it comes down to three things from elementary mathematics. And those three things, first is fractions, which I call in chapter 3 the F word of elementary mathematics. And then there's also the element of multiplication facts, of really struggling with that. Or I just surveyed a bunch of seventh graders. I said, what topic do you don't feel like you're a math person? What topic did you feel like took you out of the math game? Over a third of them said long division. We can easily break down some of these barriers for these students, but we just have to be sensitive to the challenges of it. Unfortunately, there's so much emphasis right now on reading instruction. We have administrators who are not emphasizing mathematics. Math is everywhere, not being reduced by technology. It's being increased in terms of our desire and our need for it.
Patrick, where can people find out more information about you and the work you're doing?
I'm about to start a consulting company called Elevate to Excellence, and I'm building this out because I have teachers asking for resources. I also have a blog, sullycanblogspot.com, random thoughts on mathematics. I did set up a Teachers Pay Teacher site because that seems to be many times the easiest way to read teachers now. And for simplicity's sake, I've called it See It, Say It, Symbolize It.
Thank you so much, Patrick, for your time today. This has been a very interesting conversation, and one that I hope helps math teachers reduce their anxiety in teaching math, so our students reduce their anxiety and see themselves as math students. Patrick, thank you again for your time tonight.
Thanks, John.
Thank you for listening today. I hope you got some great tips that you can bring back into your teaching. Remember, have a life teaching without sacrificing your own. Also, don't forget to subscribe and be well.